Hey everyone, I'm David Room. We've got an interesting project here tonight. I've been working for the past few days on some capabilities to do better wireframe visualizations of meshes in my game. And I had put off doing this for a long time because it takes some capabilities that I don't have written up yet to implement this. But I realized that I do have these capabilities just as part of my mesh processing pipeline, not as part of the game code. So I was able to implement it, test it out. It looks great. I'm happy with the results. So now it's time to rewrite some mesh processing stuff that uses some libraries that I don't want to package with my game in kind of pure Python code. And I thought that this would be kind of a good exercise to do in a live stream because it might be interesting for people who are learning about um, Python data structures, or just thinking about triangle meshes and maybe how you do some interesting operations, solve some problems, and a little bit about. It's also kind of interesting because it kind of gets into how some of the data is stored for the game. There's some unexpected things that I learned when I was working through things the first time. Uh, So yeah, we're gonna dive into this, and I'm gonna start just by showing kind of what I have so far, what the issue is, why we need to rewrite things, all of that. So let me share my desktop here. Ooh, that is the wrong desktop. Let me see if I can fix that. Um, it never ceases to amaze me how flaky OBS is. Let me actually tell you what. I'm going to stop streaming and then I'm going to start again in just a second. Okay, we're back. OBS seems like very good software, but sometimes it does these kind of unexpected and weird, kind of uncalled for things. And in this case, it seems to have forgotten which monitor I share with the desktop share source, which is the internal monitor of the laptop, which doesn't go away, right? So that's odd. Oh well. So I was just running this in a 9:16 mode. We'll switch it back to 16:9. Gotta brighten my display a little bit for myself here. So when we look at the ship viewer, first glance, everything kind of looks the same. I'm gonna get the dock or whatever it's called out of the way here so we have some more room. And but we have some modes that we can cycle through now when we hit the I key. So with the first one, we get this nice wireframe overlay. We also have wireframe overlay over a perfectly black material for the ship. And then we have like a transparent thing so you can see all of the individual components as wireframes. I think both of those look pretty cool. And then I was kind of inspired to prioritize this by a tweet that I saw where somebody was talking about orthographic wireframe stuff. So I also added some logic that swaps the camera out for an orthographic camera, and you can get the same views with an orthographic camera. That's kind of interesting for debugging, and it gives you a little bit, maybe a better sense of how big the different parts of the ship are relative to each other. But part of the reason that I built this ship viewer is because I wanted to use it to look at ships in game as I design them. And in game is a perspective camera, not an orthographic camera, so maybe the orthographic view isn't the most useful. But that's it. And just the thing that I want to point out here, the problem that we're trying to solve is that these edges are not, they're not all of the edges in a mesh, right? So when we are making 3D meshes for games and stuff, usually they're triangle meshes. So whenever you see a face that has more than 3 sides, that is actually made up of multiple triangles. Like all of these quads here that make up the drives, each of those is 2 triangles, right? So there would be another edge that runs down that. And it's pretty easy to turn on wireframe view and get that, but it looks very cluttered and not nice. And I think it's much nicer to look at a view like this, where basically we are just highlighting all of the edges where the angle between the normals of the faces that are connected by that edge is greater than, essentially greater than 0, or a very small amount. So that's what we want to do, and that's the thing that's a little bit non-trivial, is given a mesh, and we can extract the mesh from the 3D models that we're loading, so we can build something in the game engine that can kind of work on any mesh that we throw at it. We want to be able to find those edges. So let's take a look at how this is being done right now. Let me just close all of this stuff. We don't need all of this. We can open up what we need. So I added some functions here in the viewer, module, and it's actually all in here. So what are we doing here? So basically given a Panda 3D model, which is expressed as a node path. Node path is kind of a pointer to a node in the scene graph that can contain a whole bunch of stuff. We iterate over it. We find geom nodes. Geom nodes contain geometry. We ignore laser beams. We're going to look at all of the vertices, decompose it into a set of vertices and a set of faces, and then build a mesh out of it. And this is where stuff takes a turn that we don't want to have. So here I'm building the representation of a mesh that I use in my mesh processing tools, which is a tuple of numpy arrays. We have a numpy array that's n by 3 or m by 3 of vertices, vertex coordinates. So it's a 3D floating point vector or point for each vertex. And then we have another numpy array that's n by 3 of face indexes. So it's the index of each vertex on each triangle. And this isn't the best because even though I've written this code and it works, it uses a lot of things that I don't want to put into the game. So I have this function called wireframe info, and what am I using? I'm using numpy, and that I don't want to bring in. And we're also using the trimesh library, and that I really don't want to bring in. So trimesh is great. I use it for a lot of things that I don't want to implement myself. But there are some weird dependencies, things that generally work weird, and it's not really meant for real-time graphics. And these things we should be able to implement ourselves. So what are we actually using? So what we're doing is we're finding the edges that and I talked about this a little bit before, we're finding the edges in the mesh where the angle between the face on either side of that edge is greater than a certain threshold. And then what we're also doing is we're finding the boundaries, because what we're going to see is each individual mesh in this ship, or collection of meshes, is actually composed of several meshes that have distinct edges, and those distinct edges are the discontinuities in the shading. So basically, when you see the smooth shading, wherever there is a discontinuity in that smooth shading, that's actually the edge of a separate mesh. So we want to also highlight those edges, right? So that's the set of edges that we want. Then given those set of edges, then we can build the Panda 3D geometry with this line segs object, and then we set some properties and attach it to the parent mesh that that we're deriving it from. And just a quick note, I mean, you might think, okay, why are you doing this in the game engine rather than it being something that you could you could do at the time you're generating these models, is derive these wireframes. So I could do that. I like the idea of having it be in the engine just for flexibility, and I don't have a good way in mind to sort of store that parallel set of wireframe meshes. I don't really want to have to store that along with every mesh that I am creating. I don't want to have an additional wireframe set thing. So this is what I'm going to do, and I think it'll work just fine. And I can cache these, I can create these when models are loaded or at different times in the engine, so it doesn't have to be a real-time thing that these things are derived. I just don't want to have to store them separately. And I think, if I know what's involved in writing this, I think it's not going to take too long to implement this edge finding, or like crease edge finding and boundary edge finding in pure Python. So shouldn't be too big of a deal. We'll see. Knock on wood. Okay, so the first thing I'm going to do here is I'm going to factor out the current method so we can kind of swap it in and out with a new method that we're gonna derive. And I'm going to turn some debug visualization stuff back on and show you what it looks like as we're finding things. So I'm just gonna change this here. So we're gonna make our all edges lists here, edges, and this is just some debug visualization code. Okay. And what we're gonna do is we'll have a list of vertices and a list of faces here, and basically all of this will be in the find wireframe edges function. So all edges equals find wireframe edges of these faces. So make this new function here, find edges faces. And then this should let us move all of these imports, and these are basically all of the imports that we don't want to actually import in our final game. And I'm going to rename this to have an NP suffix, because this is what we're gonna be trying to get rid of. This is a list, this is a list, and the result is a list. And we won't bother filling in the types because we've got better things to do. But okay, let's just make sure that this works now. So I'm going to turn back on the debug stuff. So find wireframe edges NP. So we'll turn this on, and then when we run this now, as we're constructing parts of the ship, just move this off here and move. Okay, so nice. Doug Weiss says spot check wireframe not using the default mesh. No, so that's the interesting thing about this is that, okay, so I see this is why I'm gonna move this into the function as well. So yeah, the reason that it's not is because the original mesh is a triangle mesh, and the mesh that I want to visualize is actually not a triangle mesh, but a mesh that has sort of arbitrary polygons and arbitrary faces. So we want to toss out edges that connect triangles that are basically have no angle or a very small angle between them. So that's kind of the trick, and that's what we're going to be writing up today. So, and I will show you, I can actually show you here what that looks like. So yeah, so like here's our edges that we've derived using our original method now, which we're going to rewrite. So there's our edges. I will bring up so here is the actual mesh, the triangle mesh, and you can see every face that has more than 3 sides has these, you know, extra lines, and that's really noisy and not what I want to look at. We can actually what we'll do first is we'll write up sort of a dumb version that just returns all the edges, and we can see how that looks, and we'll compare it, and I think it'll be a good illustration of why we want to do this. Yeah, not line drawing-esque like some of those opening shots. Yeah, exactly. This looks very artificial. I feel like the wireframe looks like a drawing. You know, when you get rid of those extra lines, it looks like a drawing that somebody would make, which is kind of that blueprint, drafty kind of drawing look that I'm going for. Okay, so let's just write a new function, and we'll just start by basically returning every edge. So this will be our new find wireframe edges function, and take in our list of vertices, list of faces, and I'm just gonna confirm that what is going into this is something reasonable. And because this is either a panda thing or just a pure Python thing here. I don't know how much it's going to matter, but we're going to bring everything into like pure Python data structures for what we're doing. So we'll just exit right here. And I'm going to split this. So swap over to the new function. Let's take a look at what we have here. Okay, yeah, good. So these are just both tuples, which is exactly what I want. Exactly what I want to have here. Okay, so there's going to be a real quick way that we can get all of the edges. And we kind of want to do this anyway because we want to build a data structure that maps edges to different things. For starters, though, we can just make a set of all of the edges. So we'll make our set, and then we'll iterate over our faces. And we're going to sort each face. So the indices go from smallest to largest. We don't want this when we're finding normals, which we'll do in a little bit. But we want this now when we're finding unique edges. And so A, B, and C face, and we're going to add A, B, B, C, and then we're going to do A, C, because we want each of these to be in sorted order. Actually, yeah, we want each of these to be in sorted order here. Now, at the end here, we can return a list, turn this back into a list. And why are we complaining here? Okay, good. It's not complaining. Now, this should give us that, basically that original wireframe. Let's see if it does that. Yep. Okay, perfect. So this is the look that we don't want. We want to have a nice clean look that doesn't have all of these extra lines. And I like something in particular that kind of sticks out to me is sort of bad about this is these round shapes that don't have like you can see some of the shapes have like a center point. Others of these just are sort of triangulated kind of randomly. It just doesn't look nice. All right, but we're at a good starting point. So what we're gonna do now is we're going to build a couple of data structures. So what we want to build is we want to build a data structure that maps edges to face indices. And when we have that data structure, we'll be able to find a couple things right away. The easiest thing that we'll be able to find is we'll be able to find boundaries, because those are edges that have only one face associated with them. And then we'll also be able to use that to check because each edge should belong only to a pair, like either to one or two faces. So the ones that belong to two faces, then we can check the normals. So we'll have to build another data structure of faces to normals. We'll be able to check the angle between the two normals and decide whether we want to keep them. So let's get started with that. So edges to edge to faces. I always like to name maps with 2 in them so you know what they're being mapped to. And let's just do this for so here's our current set of edges, and these tuples. Okay, and then we can just for edge and edges cur all edges dot add edge. But then we're also going to do something else here. So we are going to update this guy with a list of indices that are associated with that edge. So we have to add an edge or an index here. So we're going to enumerate faces, and then for edge, actually we can do it inside the same loop. Look at that. We can say edges to faces, and then here's where we're going to use this function called set default, which always trips people up, but this is basically saying we're going to use the edge as a key, and then we'll say face, let's see, we'll call this face. So what set default does is it says, so the first argument is a key, and then the second argument is a default value. So if this key is not in the dictionary, then it assigns this default value into the dictionary with that key, and then in either case it returns the value that's associated with that key. So basically, the first time we hit an edge in the dictionary it's not in there, it's going to initialize it with an empty list. The next time it'll find it, and we will come back with it. Now let me think about this. I actually don't want a list. See, I don't want a list, I want a set. There is a possibility that there's some degenerate stuff going on in here, and I think, yeah, we just want we want a set because we don't want to have repeated stuff. So I'm going to just close the door quick here. It's turning into summer, so my air conditioner runs now. Never a dull moment in the basement. Always something running. Okay, so now current face indices, we can add our current face index. Now, once we're done iterating over our list here, this should have some properties. So I'm just going to check something here. So for edge face indexes in edge, and I'm going to call this, I'm going to rename this and just call this actually, yeah, edge to faces is fine. we want to assert, we're going to assert that the length of face indices is either 0 or, let's see, either 1 or 2. We shouldn't have any edges that don't belong to a triangle, because that's where we're getting the edges from, is triangles. And we shouldn't have any edges that belong to more than 2 triangles, because this is, all of these meshes should be nice, you know, not necessarily like manifold, not necessarily closed, but should be nice surfaces. So we'll check that and see what we get. Okay, no errors here in the ship, so I'm going to assume that it's going to work for everything else. All right, so now we can do something interesting. So now, we can return something different. So instead of returning a list of all edges, we can return a list of edges that have only one face, and that should get many of our outlines. So let's try to return this. So I'll just change this actually to be res. We'll comment that out. So we'll do instead is res is a list of edge for edge face sees in just the faces dot items if the length of face indices equals 1. Let's see what this looks like. Okay, so yeah, okay, so this is, you know, this is very close to what we want. So this is all of the places that have discontinuities. The question is, what does this miss now? Well, this misses the edges of smooth areas. And if I was getting really clever, and I might do this someday, is we could write something that runs in real time that like picks out the edges that are, you know, kind of on faces that are currently going back to front, and just highlight those so we can have this nice smooth, like no lines areas here, and like say only have an edge that kind of went across. But I do like how it looks to have the full set of edges for each facet. So to do that, we have to look for edges that where the angle between the face normals exceeds a certain threshold. So let's write that up. Okay. All right. So basically what we want to be able to do here is, instead of this simple if here, we want to say if the length of the face indices is 1, or we want to say something like the angle between face normals of face indices 0, face one is greater than some small amount. And what did I use here? Yeah, like this. Like 1 degree, basically. Okay, so what do we need to write this? Well, we need an angle between, and as it turns out, we're actually probably don't really need an angle between, but we do need this face normal. So how do we build this? So we can actually let's do this in the same loop here, because we've got our face indices. And I'm going to use this notation here, face normals. It's this, so this will be like, we'll just remind ourselves of what's what. To face index, and this is going to be a face index to a normal tuple. Okay. So now we get to do something here before we sort the face. So, say face normals of face index equals, and how do we want to do this? So we want to say the normal given the basically vertices of face 0, face 1, and face 2. Actually, we'll just call this triangle normal. And here we want to do this before we sort things, because I'm assuming that the face normals are in an order. So usually they're put in counterclockwise order, so you can tell what the outward direction is. So let's implement this guy now. It's kind of fun to write all this stuff in pure Python. I'm going to test myself a little bit here, how much I can get correct, just memorized. Angle normal of A, B, and C. So these are going to be tuples, and we're going to return another tuple. So how do we calculate the normal of a triangle given its 3 points? Well, and for people who don't know, the normal is like if you have a surface, a normal is the vector that's like a unit vector that's perpendicular to that surface. Well, what we're going to do to calculate the normal is we're going to look at, we're going to do a cross product between two vectors that we form from differences between the 2 points. So we'll do this cross product. That'll give us a vector of some unknown magnitude out from the, in the normal direction, which we then have to normalize. So that's how we'll calculate the normal. And I'm not going to use numpy or anything, so I'm going to write the cross product and stuff myself. So we'll call this, let's see, we've got A, B, and C for our points. Actually, maybe we'll call these PA, PB, and PC. Then we'll just call So now this is where we have to think about the orders. So just gonna draw a little picture for myself here. So we're expecting these points to be in counterclockwise order. So I think we want B minus A for the first one, and then C minus A for the second one. So PB and we're just going to write a bunch of fun little vector math things here because I don't want to repeat myself. So what does our subtract look like for two vectors? It's just going to be the element y's element y's subtraction whoops, one too many. Okay. So we've got our two vectors now that kind of describe the plane of the triangle. Now we need to do a cross product between them. So we'll call that guy N. This will be cross A to B. And then we'll want to normalize it. So we might as well just write a norm as well. Call that V. So what else do we have to write here? Cross B. And we need a element y's division for the normalization. So scalar basically divide vector by a scalar. N equals div n of norm of n, and then that is that. And if we implement this, we should be able to get this working because we don't actually need to calculate the angle between. We can just do like a threshold of a dot product. So actually we should do that too. So we want to do a dot product. And you know, some of this I could do with Panda 3D built-in stuff, but I'm kind of on a roll and I'm having fun just writing this up from scratch. So we'll just implement all this stuff. Okay, so let's go down and actually we'll just do this right here. So this will be if the dot is greater than some thresh here. And like, what is our thresh? Well, I mean, the dot product is just the magnitude times the cosine of things. So we could do what do we want to do? We want to do, it's like times the cosine of so yeah, so the threshold is just going to be the cosine of that this thing that we wanted. So okay, let's write all this up as quick as we can. How far are we in here? We are 45 minutes. Let's see if we can get this working in 15 minutes. Okay, so this a dot product is just the corresponding elements of two vectors multiplied together and summed up. I still, you know, the funny thing about the dot product is I have a pretty good intuition at this point for like what it means, but it's very hard for me to picture and be comfortable with the fact that this operation of like multiplying corresponding elements and summing them up does the thing that the dot product does geometrically. But that's my problem and not anyone else's. So that's easy. Division, this is just element wise. V0 divided by S. Oops. Zero, V1, V2. And actually, instead of division, let's just make this multiplication because we can invert the scalar element outside, and multiplication is just nicer. So we'll multiply it by 1 over the norm, right? That's the same thing? Yep. Yeah, Doug Wise says, dot products taking me back to undergrad. You know, it's one of those things that it's like I learned about in school and I just could never picture, the geometric meaning of it as far as like capturing the projection of one vector onto another. I could never picture that until I started doing this kind of stuff for my work. And then it's like, oh wow, that's a powerful operation. Okay, so, and then the normal, do we have math imported? Yeah, so the normal is just going to be the square root of the sum of squares of things. So if we're feeling kind of a nice way to do this actually would be a dot of v with itself. So that's kind of nice. And then the cross product. Let me see. So I at various times I've had this memorized and not had it memorized, but I think I have it memorized right now. So I'm just going to try to write it out without looking it up and see if I get it right. So the funny thing with the cross product is, hey, got Balvir in the chat, hello. So the trick here is with the cross product, you have this kind of, answer my message. I don't know what you're asking for. We have this alternating product where we multiply a couple things together and then subtract kind of like the opposite order. So let's take a look here. I don't know what you're talking about a message. You got to ask me a question if you want me to answer. Okay, so let me see here. So basically we have 3 element vectors, right? So each element of the cross product is this alternating multiplication and subtraction using the other 2 elements of the vector. So the first element is going to be A1 times B2 minus A2 times B1. Hello, Rohan Gaming. So then we basically just continue the same pattern using the other two. So instead of 1 and 2 here, it's going to be 2 and 0. So 2 and 0, 0 and 2. And then here it's going to be 0 and 1. 1 and 0. So kind of going forward here, going backward here. It's tricky to remember this sometimes, but the key is just that, you know, ordinary multiplication is commutative. So it's you're not simply swapping the order of what you are multiplying. You're swapping the order of the indices. That's the important thing. Hey Arnab, I am from Wisconsin in the United States. Where are you from? All right, so let's see if this works. We've implemented now subtraction, and cross product, norm, scalar multiplication. It's kind of funny that we didn't do addition, really, but that's okay. And I see a little typo there. That would have tripped me up for sure. But let's see if this works. I have very high hopes that this is going to run and produce the results that I expect on the first time. So let's see. Hey, no problem, Arnab. I am from the United States, from Wisconsin. Where are you from? Very high hopes that this is going to run, and I don't see any typos or anything. So let's try it out. So we have our two conditions, right? Boundaries and edges that have that that dot product that is greater than the threshold. And let me just think about this. Do I need... I might need an absolute value on this, because I want to capture both things that are inside. Let's see here. Let me think about this, because the dot product is going to be 0 when things are orthogonal. Oh yeah, maybe this isn't quite what I want. Oh, no it is, because when... Oh, okay, no, this isn't what I want. So I want a dot product where I want where 1.0 minus the dot product is because like for two faces that are pointing in the exact same direction, the dot product is going to be 1. Actually, let me just think about this for a second. Okay, so yeah, my threshold is going to be that, and this will be either, this will be positive on either side, right? Because cosine is symmetrical and it's all positive around 0. So what I actually want is I want to keep this. I was right. I was right in the beginning. So what I'm picturing here is, like the cosine function it's like a hill, right? And that hill is, the top of the hill is at 0, a 0 degree like angle between those two vectors. And whether our angle is a little bit positive or a little bit negative, the dot product is gonna be the same. It's symmetric on either side of that cosine. So what we want is something. We want something. Actually, we want something less than the threshold. Still not quite right. Yeah, we want something less than the threshold because if it's greater than the threshold, that means it's close to flat. As the cosine decreases, the cosine decreases as the angle increases. All right, let's run this. See if it works. Nope, didn't work. So set object is not subscriptable. Where are we subscribing a set? Oh, here we go. Oh, that's why. Okay, because face indices is a set here. So I'm gonna just quick turn this back into lists with a dict comprehension. So okay, list v in edges to faces. So that should take care of that. Whoop, and not edges to faces, but edge to faces. Can we finish? Boom, there it is. Perfect. Look at that. Now, do I see anything goofy here? I don't. There might be some ways to double check this against the original version to kind of like make sure that there aren't any differences. I don't really feel the need to do that right now. This is primarily like a visual thing. So I'm just going to take a look at a couple different ships here and see if it looks good. I'm not seeing anything that looks like anything that I don't expect. So that takes care of that. Now, a couple of things that we could change here if we wanted to would be to replace this stuff with the Panda 3D built-in stuff. I don't feel the need to do that right now, and it was kind of fun to write up. And I think it's kind of fun to have stuff like this in your library just for when you need it. So we're gonna call it here then, I think. So just to kind of review what we did, we had this original version of our, I would say, relevant edge finding function. Frame edges p that used numpy. It used some functions from trimesh for finding angles between normals. Enabled this functionality. I don't know why this is all of a sudden taking. Oh, what is it waiting for? Oh, I know what it's waiting for. I'm visualizing meshes yet. It works. But we wanted something that doesn't use numpy, doesn't bring these other dependencies in, so we wrote our own. And it actually seems to run a little bit faster, which is not surprising because that wireframe stuff is finding some extra things that it doesn't actually need. So yeah, I call this a win. Yeah, I mean, again, like I said, I think we could rewrite this to use use the built-in Panda 3D stuff. There's really no reason to do that at this time. Actually, we can even move all of this stuff in there if we wanted to. There's really no reason to do that at this time. This stuff is all pretty bulletproof and seems to work well. So, thanks for watching. I think we did something kind of fun and unique and interesting here, writing a little bit of mesh processing code rather than using a library to find the stuff. We kind of got our hands dirty with a little bit of linear algebra, vector math, and implemented it ourselves. I'm a little bit surprised that this worked so well the first time. I thought for sure that there'd be a typo somewhere, but whatever I wrote works well enough, so we're gonna not look a gift horse in the mouth, I guess. But thanks to everyone who's watching. If you're interested in this project, it's a retro space combat game that I'm writing in Python. Interesting part about the way I'm building this project is that all of the game content is actually also created with Python code, so I have a lot of custom mesh processing code for creating the 3D models, and I was using some of that here for this this wireframe visualization, but I wanted to rewrite it so that it wouldn't be included in the game code itself. But yeah, I have a lot of previous live streams where I'm modeling things live, doing other game stuff. I also have another series that I'm doing where I'm building a retro, much more retro, like 1970s microcomputer style survival game, kind of inspired by Oregon Trail, but set in my cool sci-fi horror universe. So check that out if you're interested. And I'm gonna call it here for tonight, but thanks again for everyone who's watching. Thanks for coming, Doug, and everyone else too. So have a good rest of your night.